Good morning.
Morning, sir.
Yeah, welcome back. I just want to uh, quickly go through what we have done in the previous class, and maybe I'll show you some MATLAB simulations, and then we'll go to the next topic. The slides visible.
Yes, sir.
Okay. Previous class, I think we discussed about the sharpening spatial filters. So we also looked into the difference between first derivative and second derivative. And a typical example was taken where you have some ramp edge, you have a isolated point, you have a thin line segment, and you have a step edge. And then how first and second order derivative responds to this, we have just observed various differences. Uh, One of the major difference is the double edge effect that you will have in second order, which was not seen in first order. Another thing is response around the noise point is much stronger in the second order. Okay, so in fact, during when we discuss about segmentation, when we are trying to identify points, we are going to use this double edge, sorry, the second order derivative. So we will discuss this again there. So we went to the first principles and wrote the expression for the Laplacian, and we saw this is one of the Laplacian filter. And if you want to consider the diagonal edges, we will just modify it here. The center pixel can be even taken as positive and other values negative. So even these two are also okay. So this is called a Laplacian mask, and we applied it onto an image and we saw the results. Then how this could be helpful in improving the edges or crispening the edges we saw. If you just add the original to the Laplacian, we will actually get this Laplace, in fact, edge crispened image. You could see this result. Okay, so we'll see a demo of this also. So the kernel would be like this. The center value is 5 and the other values are -1, or the center value is 9 and other values are -1. So the results are seen here. And we also saw a concept called unsharp masking, and this is done by just subtracting the average from the original and add either exactly this to the original, or maybe you can just scale it by some amount. So you could see the sharpened signal, and the results are shown on a specific image here. So this is what we discussed in the last class. So before going to the next topic, that is gradient operators, let us just go to the MATLAB. Is the MATLAB window visible?
Yes, sir.
Okay. So I just want to start with actually a median filter, in fact, which was discussed, and all of you know median filter is one which is going to remove salt and pepper type of noise. So I'll just run this part of the result. What I'm just doing is, if you carefully observe, MEDFILT2. This is the command to run a median filter of size 3 cross 3 on an image. So let us see the results. What you see here is, this is an image. Carefully observe, there is a 255 here, there is a 0 here. So I said, if on an image, if I have a very bright pixel or a dark pixel isolated like this is usually a salt and pepper type of noise. So if I run a median filter on this is what you get. Observe, this 255 is replaced by 18 here, which is actually the median of these 9 pixels. We took an example in the last class, and you know median of these 9 pixels would be 18. And also observe, this 0 is replaced by 16 here. Sorry, not 16. What is the value? Yeah, so third, fourth, fifth. Yeah, 16. So if you look at the median of these 9 pixels, that is 0, 12, 16, 16, etc. 13, 16. 16 is the median. So you could see that median value is replaced. So median filter can remove salt and pepper type of noise. This is one simulation I just wanted to show. Then you can apply this median filter on an image. So let us see this result also. So I'll explain one by one. The first figure is your original child image. Is the image seen? This is the original image.
Yes.
Okay. The second is actually the histogram of that original image. So what you notice is the pixel values are distributed from 0 to 255, and particularly you have more pixels of range 100 to 200. That's okay. This is just to see the histogram. And the third image is actually an image with salt and pepper type of noise. So you can notice white dots and black dots here. How it is done is, if I just show you the code, because you should know how to add this noise. So observe here, im noise is the command, X is the image, and if you want to add salt and pepper type of noise, this is how you have to give within quote salt and pepper, and this is the probability 0.05. So if I change this probability, the noise that gets added also changes. So you could observe that the image is corrupted with salt and pepper type of noise. And the next is the histogram of this noisy image. So carefully observe here. Uh, Originally, whatever you had, all the values are there. So you should be noticing that at 0 there are pixels. So you should see a blue line here. And also at 255 there are, so these are the noisy pixels that I have added in the image. So you have many 255s and many zeros. That is why it looks like this. Now when I apply a median filter on this, observe this is what has happened. So this was your noisy image. This was a noisy image, and after filtering this is what you get. So you can carefully observe noise is removed, that is salt and pepper type of noise is removed, but also just observe the text region here. Okay. Look at the original text and look at after filtering what has happened. So because when median filter is applied on this type of data, even the edges also look like salt and pepper type of noise. So you could see that it has the text region is slightly spoiled. So if you apply this again and again, then you will have the problem. Okay. Suppose if I apply an averaging filter, observe that instead of improving the image, it has actually spoiled it. So averaging filter cannot be used for salt and pepper type of noise. If I increase the uh, size of the filter 5 cross 5, how I have done, just look at the code. So here I am providing the dimension here, median filter of size 5 cross 5. Okay. So a median filter applied again and again will spoil the data. That's why I said median filter once or twice is okay, but don't do it beyond that. Now let us look at the uh, high pass filter. So I'll just run it on this. So you have so this is a cat image. Original image is this. So if I apply a high pass filter, that means a Laplacian on this, this is what you get. So you could see that the edges in the image are detected. And if I use the diagonal neighbors also into consideration, you can definitely see the edge information is more now, obviously, because even in the diagonal direction also they detect. So like this you can apply many type of filters. Okay. Now edge crispening also I'll just demonstrate. So let me just run this. Now notice the first image and the second image. This is the first image. Okay. Keep observing the edges, like particularly this small okay, edges that you observe here, just see it has improved here. So what I have done here is, if you observe the code, not great thing is done. So the center pixel is 5 and the 4 neighbors are -1. That's what I have done. So what you notice is, this is what I have used. Center pixel is 5 and these are -1, -1. So if I just do a convolution of this type of kernel on the image, I get a more sharpened image or edge crispened. So this would be helpful in better detection of objects. Okay. So with this, let us just move on. Okay. So yeah. So the next thing is, using gradient where you make some approximations. Okay. As you saw, we took gradient along x direction, and gradient along x direction is by differentiating along x direction, partial differentiating. Gradient along y direction, and just take the magnitude of that. This is how you did it. Now, you can just approximate this equation as mod of gx plus mod of gy. This is just an approximation. So, how do I get this gradient along x direction? I just take the difference between the two pixels. Z8 and Z5 is referring to this image, this picture. Z8 is this, Z5 is this. So, if I just subtract these Z5 from Z8, I am getting the variation or the edge along x direction. If I do Z6 minus Z5, I'll get the variation along the y direction. Okay. So I will just use this type of operator. Suppose if I just do Z9 minus Z5, then it will be giving me the variation along this diagonal direction. Z8 minus Z6 will give the diagonal variation along this direction. So these are also various filters that we use. So just observe here, 1 minus 1 here means I am doing Z9 minus Z5. 1 minus 1 means I am using Z8 minus Z6. So I get variation along this direction. So these type of filters where you just subtract the neighboring pixels like this, they are actually called Roberts gradient operators. Please remember this name. These are called Roberts gradient operators. Then by slightly modifying them, another person, Sobel, has given some variations where you could observe that the center pixel is weighed more compared to the other pixels. So 2 here minus 2 here, 1 here minus 1 here. So this will give me variation along x direction, and this will give me variation along y direction. You can try simulating this by just running this kernel on an image. You will get it. So for want of time, I may not show it. Same code that I showed. No, you just generate this kernel, convolve this with the image. You will get variations along x direction. Do the same thing with this. You will get variation along y direction. So if I add both of them, I will be actually getting the edge information along x and y direction. So I repeat, these type of operators or mass, they are called as Sobel gradient operators, and Roberts gradient operators. And these type of operators where the center pixel is weighed more, they are called Sobel gradient operators. Okay, so please remember this, and we are going to use these operators during our segmentation in fourth unit. Okay, so this is about the spatial domain enhancement. Is there any specific question on this? If there is anything to be clarified, I'll do it. Otherwise, we'll go to the next topic. Any specific doubts about the spatial domain filtering? Because the next one is frequency domain enhancement. Okay. Of course, this is an example of the previous one. I think I have already given these type of examples. Okay, so since there is no specific question from you, okay, at least uh, can you tell me who is this person? Can somebody say who is this person? Hello? Is my voice clear?
Go for
Is it clear?
Yes, sir.
Yeah, yes. Who is this person? Is it such a difficult? You not seen this photo any time? We have put it in our lab also. Okay. I think definitely he is the person who is responsible for whatever that is happening in our signal processing. He is Joseph Fourier. We have discussed about Fourier transforms, and he is the one who actually gave this Fourier analysis. And I think a lot of things are discussed during your third semester's DSP and also DSP. So please at least remember this ways, because we have put this photo in our lab also. Okay, so I don't think I need to read all these things. That is why I have given this as a slide first. From here to the 15th slide, it is self-study for you. So I will just quickly go through them. This is brief details about what, okay, about Fourier, and also what he told, what is a Fourier series, what is Fourier transform, and I think this is what Fourier told. If I just take various frequency and a magnitude sinusoidal signals, add them up, I'll get an arbitrary signal. This is what Fourier told. So please have a look at these slides later. And I think during first chapter we have discussed about Fourier transform. So there are some formulas here. This is the two-dimensional for DFT. We think I think we have looked into this. This is the inverse DFT, two-dimensional. How we can represent by using polar form. How we can do magnitude spectrum and the phase spectrum. How to find the power spectrum, and how to find the average value of an image. Okay. So some properties like convolution, correlation, separability, I have discussed about it. Separability is two-dimensional DFT can be computed by using two one-dimensional DFT. That's separability. How we can obtain the inverse Fourier transform using forward transform. Okay. Various other properties like shift in the frequency domain, the corresponding image gets multiplied with an exponential. Shift in the spatial domain, the corresponding spectrum multiplies with an exponential. Okay, and a small variation to this is, suppose if I make u naught equal to m by 2 and v naught equal to n by 2, if I substitute these values here, you will actually get this as minus 1 to the power of x plus y. So this is actually, if you remember, I introduced a command called FFT shift when I was showing you the Fourier transform of an image. So this actually does that FFT shift. That means shifting the Fourier transform to the center. And there are many other properties. Please have a look at these properties. Okay, this is only for your understanding of two-dimensional Fourier transform. So this is the concept of FFT shift. When I show an image, this is one-dimensional FFT of a rectangular pulse. You can see that at 0 you have maximum, and even at this value also you have maximum. So when I look at this window, as you can see, the magnitude is decreasing and again it starts increasing. So when you see an image, that is how it looks. So the at the corners you will have the maximum magnitude frequency. That means your zero frequency components. So if I shift it to the center, it would be better for visualization. This can be done by using a command called FFT shift, which I told you when I was discussing about Fourier transform. You can see that this point is shifted to the center. This is shifted to the center. All these things are shifted. So I have at the center maximum magnitude, and as I move along, it is decreasing. Okay, let us not worry about these things. This is a rectangular pulse, how it can be shown as an image. Another rectangular pulse shown as an image. If I shift it, shift in the spatial domain, the magnitude doesn't change. So you can observe that the magnitude remains same. Rotation in the spatial domain, the spectrum also gets rotated. This is another property. And this is how you can represent Fourier transform of an image. And I think I told you, if I just show the Fourier transform of an image as an image, and remember we used a transformation to display the Fourier transform of an image as an image. Can somebody recollect which transformation function is used to display the Fourier transform of an image as an image? One of the transformation functions that we used. Anybody? Anybody who can comment? Which transformation function I use to display the Fourier transform of an image as an image? Okay, I think I have to answer it since nobody is answering. It is logarithmic transformation. So what you notice here is once I do that Fourier transform as displayed as an image, dominating white lines here indicates the frequency is varying in this uh, okay direction. For example, if I move along this direction, definitely the pixel value, gray values are changing drastically. Even if I move along the diagonal direction also, there is a drastic change. But if I move along the x direction, not much you can observe. So this is actually the uh, similarity between Fourier spectrum and its spatial domain representation. Now, as I told, magnitude and phase, they are going to carry a lot of information about the image. And in fact, phase is going to carry the maximum information. So to demonstrate that, what is done here is a woman image is taken, and you can observe that the phase is displayed here. There is lot of changes in the phase. Now only by using phase, that means the magnitude is made equal to 0. If I reconstruct the image, you can observe that you can at least see that there is a woman image here in this. Okay, so that is the meaning of what I said. The phase is going to dominate. So phase is going to carry a lot of information about the image. Now suppose if I reconstruct the image only by the magnitude, this is what you get, and definitely I don't think you can say this is image of a woman. You cannot see that there is a woman image in this particular that is obviously true. Okay, so suppose if I reconstruct using phase angle corresponding to the woman, then you get this. If you I think this I can demonstrate using uh, a MATLAB simulation, maybe sometime later, not now. So where you can just take the magnitude of one image and phase of the other image. So here phase of woman is taken, that is why woman is dominating. Here phase of a rectangle is taken, that is why the rectangle is dominating. That means this is going to demonstrate that phase of an image is going to carry maximum information. Okay, yeah, I think from here it's very important for you. Till now, this is actually the self study for you. I hope you can just have a look at this topics. Now, how do I do uh, frequency domain filtering? Okay, so let me just go to the OneNote. Is the OneNote visible?
Yes, sir.
So if you remember, what we did in spatial domain is we just took a kernel h of x comma y, and which could be, for example, one of the kernel that we took is the simplest box filter, 1 by 9 1 1 1 1 1 1. This is what we took. So we took an image, convolved the image with h of x comma. Convolve means applied this type of filter, and what you got was a filtered image g of x comma y. This is what you do. So since the image is in spatial domain, the kernel is in spatial domain, we performed convolution and we got spatial domain. Now suppose if somebody asks you, how can I do this in the frequency domain? All of you know it is very simple. Take the Fourier transform of this, okay, this equation. So you know f of x comma y will become f of u comma v. That means frequency domain representation of the image. What happens to convolution when I take the Fourier transform? Convolution in spatial domain is dash in frequency domain. What is convolution in spatial domain? This is a property which you have discussed even in one dimension also. Nobody wants to respond.
Multiplication, sir.
Yes, very good. So convolution in frequency domain is multiplication. So h of x comma y will become h of u comma v. So obviously I'll get the processed image. But if you notice, the processed image is in the frequency domain, but I should get back this. So what should I do? If I want g of x comma y from g of uv, I should do inverse Fourier transform. Simple. So carefully observe the steps now. If I want to do it in frequency domain, take the image to the frequency domain, take the kernel, that is the filtering kernel, to the frequency domain, multiply them. Whatever you get, take the inverse Fourier transform, you will get back. Okay, so this is all you have to do, but the only catch here is when I take the Fourier uh, spectrum of an image, as I said, you have to center it. I think I told you about this in the last class only. Yeah, so let me just go back. So observed here, when I take the Fourier transform, usually the low frequency components will be in the edge here. So I have to bring this to the center. So bringing it to the center as a property I have already told you, you have to shift the Fourier domain to the center, that is by m by 2 and n by 2. To perform that, I have to do multiplication of the original image with minus 1 to the power of x plus y. So this is an additional operation you may have to do. Okay, so let us go back now to the steps now. So multiply the image by minus 1 to the power of x plus y. So this is an additional operation. We call this as a pre-processing step. Compute the Fourier spectrum. That's what I told you already. Multiply the Fourier spectrum with the Fourier spectrum of the image, of the kernel. Okay, because convolution in spatial domain is multiplication. Now since you have to shift it back again, okay, multiply the result by minus 1 to the power of x plus y and compute IDFT of the result. Okay, this is actually minus 1 to the power of x plus y into the value. So that is missing here. So then multiply the result by minus 1 to the power of x plus y, compute IDFT of this. So you will get back the original image. So these are the steps. As you can see here, input image is taken. Pre-processing is this operation, multiplying with minus 1 to the power of x plus y. Take the Fourier transform of the image, I get f of uv. Multiply with the filter h of uv, I get the product. But you should go back to the spatial domain, so do an inverse Fourier transform. And as I said, you have to, since you have shifted it by multiplying with minus 1 to the power of x plus y, you have to do it again. So do that post processing here. I'll get back the enhanced image. So these are the steps. As you can see, when compared to whatever I explained here. Here in the spatial domain, I was directly convolving, but now I had to do it in the frequency domain. So you have to take them to the frequency domain, perform the multiplication, do an inverse Fourier transform. That's exactly what is shown here. Okay. So that is all the steps to be followed for frequency domain filtering. Now from here onwards it is simple. So you choose a filter according to your requirement. If you want low pass filter, choose a low pass filter response here. If I want a high pass filter, choose a high pass filter here. If I want to do edge crispening, choose a high pass filter, sorry, edge crispening response here. That's all you have to do. Okay. For example, a very simple case. Suppose if I take this type of filter, h of uv is equal to 0 at 0 or at the center of the okay, spectrum, and 1 in all the places. Okay, so carefully observe at the center, that means the zero frequency component is killed here. This is just a notch filter. I'm just going to kill the zero frequency component, and you know zero frequency component of any signal is the DC value of that particular signal. So if I make the zero frequency component equal to 0, it means that I am killing or I am removing the average value or making the average value of the image to be 0. That is why when you see the image, you could observe that the brightness has decreased because you have made the average value of the image signal to be 0. So observe the brightness value of the image is decreased. So this is one of the simplest filter. This is also called notch filter, where a specific frequency component is killed. So I can use the different types of filters. You can observe that this is an approximate two-dimensional low-pass filter. This is a high-pass filter. The response, I think it is looking similar to your 1D responses, but these are 2D responses. Okay, so this is a simple low-pass filter. As you can see, the edges are smoothened here. This is a high-pass filter, so you can see that the edges are passed. Okay, suppose if I just add an average, a small DC value to the high pass filter version, you can see that the average value, brightness value has increased. Okay, so there are actually many filters. I think this is again uh, just similar to one-dimensional filtering only, except that it is a two-dimensional filter. All of you know, I think this I can just plot it on the. Okay, so let me just plot a low pass filter in one dimension. So you know that suppose if I just take x-axis as frequency and y-axis as the magnitude of the spectrum, an ideal low pass filter looks like this. Okay, up to some cutoff frequency, the magnitude is 1, and beyond that cutoff frequency, the magnitude is 0. Okay, so this is an ideal low pass filter in one dimension. Now, if it is two dimension, you should visualize what should happen. Okay, so this is okay, let me just write the expression also here. So what you notice here is h of f is equal to 1, or as long as the magnitude of this f is less than fc, and it is equal to 0 when this magnitude becomes greater than or equal to fc. So this is for a one dimensional low pass filter. Okay, so if it is two dimension, we need to just extend this for one more dimension. That is what is done here. Okay. Is the slide visible? Is the
Yes, sir.
slide okay? So observe here in two dimension, an ideal low pass filter looks like this. As I said, the magnitude h of uv now, because it's two dimension, it is equal to 1 as long as the distance from the origin, that means the frequency value is less than or equal to some d naught, some cutoff frequency, If it is greater than that cutoff frequency, then the magnitude is equal to 0. Since it is two dimension, this condition has to satisfy for entire circular region. Okay, so that is why if you observe the spectrum, this is how it looks. Okay, so from the origin to up to the cutoff frequency, say d naught, you can see that all the values are 1. So 1 means it is white and all other values are 0. So this is an ideal low pass filter. This is what is known as a perspective plot of an ideal low pass filter, a 3D plot, whereas this is an image. Okay, this is an image. So this is actually image of this only. So if I look at this as an image, this is how it looks. So carefully understand, wherever you have white, those frequencies are passed. Wherever you have black, those frequencies are eliminated. Okay. So if I want to show this in a simple radial cross section, this is how it means. Up to D naught, the magnitude is 1, and beyond D naught, the magnitude is 0. That is exactly what I wrote in this case. See, up to Fc, the value is 1. More than Fc, the value is equal to 0. So for a two dimension, it looks like this. Like this. Okay. So this is a low pass filter. And now, if I start changing this cutoff frequency from very low value to very high value, you know that that means I am moving this cutoff frequency, which means that more and more frequency components are allowed. So just to demonstrate that, what is done here is uh, the radial frequency is modified. For example, hope you can see some concentric circular white circles on this. Do you see those circles here? Can somebody respond on this image? Are the circular region visible? Anybody?
Yes, sir.
Okay.
Yes, sir.
Okay. So what we do is, as I mentioned, this d naught is increased, which means this circular radius is increased from 0 to large value. So the first circle is drawn at 5 pixels. That means the inner one here. Then it is at 30 pixels. Then it is at 80 pixels. Sorry, 15, 30, 80, and 230. That means this is at 230, this region. So what you notice is, depending on this circular region, the corresponding frequencies are passed. Okay, so this is the original image, and if you apply this type of filter with a different radius, if I allow maybe the radius to be equal to 5, that means only 5 pixels here, then it actually encloses 92% of the power, and that power is calculated by using this formula. Okay, so 92% of the power, that means even though the radius is very small, you could see that so much amount of energy is passed to the output. That means, which actually says an image is actually a low pass signal. That means it has more and more low frequency components. Suppose if the radius is 15, then it passes 94.6%. If the radius is 30, then it passes 96.4% of the power. If it is 80, it is 98%, and if it is 230, it is 99.5%, because obviously almost all the frequency components are passed. Now let us see the results. Okay, observe. This is the original image. This is for radius equal to 5. So you could see that there is a severe blurring, obviously because the edge information is lost. I have removed because it's a low pass filter. This is for radius 15. At least some alphabets are seen. For example, this A can be read, whereas these things cannot be read. In this case, even these things also can be read. Okay, but notice here in this region, the noise is completely removed. You don't see anything there. Whereas if I start increasing the cutoff frequency, even the noise also starts passing through the image. If it is the radius is 80, you can see that this and this are almost looking same, and of course this is same as this image because it's almost passing the entire 99.5% of the data. So as I increase the cutoff frequency, what you notice is more and more frequency are passed, so the blurring will be decreased. Now there is an important thing that you should notice here. In these two images, it is very clearly evident. Okay. Uh, I hope you could see some type of what is known as a ringing structure here. Do you notice that? For example, around this A, you will start seeing some rings here. Is it seen? Some rings here. For example, around this A, just observe, you have some rings. Even here also it is noticed. You are not noticing this ring here, some circular region. Yes or no?
Yes, sir.
So this ringing effect is because of the ideal nature of your filter. See, actually ideal filters are no doubt good, but it has its own effect. What is that effect? Now, this is actually in the frequency domain. Okay. Now, can somebody tell me if I take it to the time domain, how does this signal look? If I take the inverse Fourier transform of this, what will I get? Can somebody tell me? Inverse Fourier transform of a rectangular pulse.
Sync.
Correct. It is a sync pulse. Okay, so this is what you get. Now observe here a sync. So which means multiplying with this type of filter is same thing as convolving the image or signal with this type of response. Okay, so when I do this type of convolution, convolving with a sync. So this is a meaning. Multiplying with a filter like this is in the spatial domain, it is convolution. So you see some zero crossings here. These are all the zero crossings. So because of these zero crossings, when I convolve this type of signal with an image, I actually get ringing effect. Because of this zero crossings, you will get an effect called ringing effect. This is the disadvantage of an ideal filter. Any ideal filter has got this disadvantage. If there is a sharp transition, then because of this sharp transition, when I perform convolution or when I perform filtering, because of the sharp transition, uh, you will see convolution with a kernel of this nature which introduces ringing effect. Okay, so that is exactly what you should notice here in the image also. It is very clearly visible in the image. Okay, particularly these two images demonstrate that a lot. So that is why normally they don't use ideal filters. They will use smooth filters, which is the next one. In fact, with this image also the ringing effect is explained. Okay, so I think it's self-explanatory. So as I said, ideal filters have got its own disadvantage. That is, it introduces ringing effect. So just to have to avoid this ringing effect, normally we go for a smooth filter, which is a Butterworth low pass filter, and but this is extension of your one-dimensional Butterworth low pass filter. So as you can see, uh, there is a parameter here n which decides about the order of the filter. Okay, so I can change this order of the filter and change the response of the filter. I think this is already known to you in one dimension. So when suppose when the distance is 0, okay, so 0, this value is 0, which means this value is 0, so the magnitude is equal to 1. That means at the origin the magnitude is 1. As I move away from the origin, the magnitude asymptotically decreases. So I think this plot is already known to you. This is how Butterworth low pass filters are shown for one dimension. So observe compared to this ideal nature of the filter. This is an ideal filter. Observe here there is a smooth. So if I have this type, I also I think this is one of the property also. This type of a smooth uh, okay curve when the Fourier transform or inverse Fourier transform is taken, it is also smooth. In fact, a Gaussian pulse, both in time domain and frequency domain, is almost is a Gaussian. So this smooth curve here definitely avoids the ringing effect. So observe the variation here. It is not a very sharp variation here. It is gradually decreasing. Now, as I change the order, the curve becomes more ideal. So higher the order, the Butterworth filter moves towards an ideal filter. This I think all of you know. For example, fourth order is like this. So if I take a 20th order filter, it may almost look like an ideal low pass filter. So this is one of the control I have. Suppose if the ringing effect is more, I can try to reduce the order of the filter and make sure that my ringing effect is removed. So observe the results here. This is the original filter, original image. This is by applying a first order Butterworth filter. Maybe if you just go to the higher cutoff frequency. Sorry, it's not the first order. If the cutoff frequency is taken as 5, this is how it looks. If it is taken as 15, this is how it looks. If it is taken as 30, 80, and 230. Let me just compare these two together. This is for your ideal filter and this is for Butterworth filter. Now, can somebody respond, particularly the second row, if you just compare this with this, what is the change? Not difficult to explain this. No difference is visible, but I'm just showing you this and this together. This is where the difference should be seen. Any comment? Hello, are you there? Can somebody chat at least if you cannot speak for any reason? I'm just waiting for your answer in the chat window. You don't want to speak, just chat. Hello, is my voice clear or any problem with the connectivity? Yeah, I think somebody responded through chat. Let me just see. Yeah, it is Shivam and Nitin Bharadwaj. Ringing effect is seen in low pass, ideal low pass filter, but not in Butterworth. Good, Nitin. Okay. So Shivam says second figure noise is reduced as compared to first figure. I don't see that effect here. You can observe the noise here, they are almost same because but what Nitin is telling is correct. So the ringing effect is not seen. Okay. So here ringing effect is not there compared to obviously because I am actually taking a Gaussian filter, a Butterworth filter, and this in the frequency in the spatial domain also looks similar. That is the advantage. Whereas if it is ideal, then you would have seen ringing effect. So you could observe that the ringing effect is in fact missing. Okay. Of course, when compared to the uh, ideal filter of radius 5, if you observe the Butterworth filter of radius 5, at least some structure is visible because the uh, Butterworth filter actually uh, doesn't have a sharp cutoff, so some portion of the signal is passed. For example, this with great difficulty you can recognize it to be an alphabet here. But when compared to that here it is very bad. Okay, Preeti is giving some, yeah, in first column it seems to be some gradient point, while the second column you see the smoothness and gradual soft, yeah, the gradual variation. We don't say softness, okay. Yeah, uh, so severity of the blurring is less here, but at the cost of that, at least the ringing effect is removed. This is an advantage. Okay, so that is about an ideal and a Butterworth filter. The last one is a Gaussian filter, which I think I have explained here only. The third one is Gaussian filter. So this is an expression for Gaussian. It's almost looking like Gaussian, as you can see. E to the power of minus x square by 2 sigma square is a Gaussian signal. So here D naught is the cutoff frequency. So as I vary this D naught, the frequency, sorry, the more and more frequencies are allowed. So this is a Gaussian pulse, and this is its image. Now when I apply a Gaussian filter, you can see that even Gaussian also doesn't introduce any ringing effect. Okay, but you can see that if I use a Butterworth filter, I have one advantage, that I can have the control on the order. That means I can keep changing the order so that the image becomes more and more ideal. So you can just have a factor compromise between ideal nature of the filter and also avoiding the ringing effect. Whereas a Gaussian filter doesn't have that control. The only control is the cutoff frequency. So I can start increasing it, thereby more and more frequencies are allowed. Okay, so you can see that as I start increasing, the output image looks more and more similar to the original image. Okay, so this is actually a low pass filter, ideal, Butterworth, and Gaussian, three types. Okay, so comparatively, ideal filter very good in removing the, in fact, noise, and also uh, it is okay, allowing you the sharp cutoff. But because of this sharpness of the sharpness nature of the filter, you would have ringing effect. Butterworth filter definitely is better compared to ideal filter. Gaussian filter, no doubt, it can also, in fact, it will also not introduce the ringing effect, but there is no control on the ideal nature of the filter. I cannot make it to be ideal by changing anything. Whereas the Butterworth filter, I have a control on the order of the filter. If you want uh, a better ideal type nature of the filter, I can have a higher order filter. Where is it being used? I think this is a very nice application. Um, suppose if you are working on maybe text recognition system, if you closely look at this type of text which is scanned, you can see that there are some breaks here in the data. So no character recognition system can recognize this as E. Human being can recognize this as E and this as A, because wherever there is a missing data here, we actually feel that. Actually, they say we see through the brain, not through the eyes. That means any missing data, I feel it, but a computer cannot understand this. So I need to actually smooth this region so that this, in fact, break should be removed. So if I pass this through a low pass filter, you can see that you get a smooth curve now. All the edges are connected. Therefore, this is better for character recognition. This is one application of low pass filter. Okay, actually in this case, I think they have used a Gaussian low pass filter. So you can see this type of application. So whenever I have this type of problem, pass it through a low pass filter. So the edges are connected now. That means the breaks are missing. Now it can be probably used for further processing, pre-processing. Another good example, I don't know on your computer screen whether it is visible. This is actually an image of a woman, and is her eye portion is shown in the zoomed okay portion here as a small region. You could observe that the near the eyes, because of the aging, you could see that there are some wrinkles here on the skin. Okay, very difficult probably for you on your uh, mobile screen to visualize that. But suppose if this has to be smoothened out, you can just pass it through some filters. For example, this is the output of a Gaussian low pass filter. This is the output of a Gaussian low pass filter. This is with the cutoff frequency equal to some 100, I think, and this is with cutoff frequency equal to 80. So what you notice is, if you compare this region with this, you would notice that it is smoothened here. Okay, so this could be, in fact, post processing of images which was done by photographers is done by using this type of technique. Okay, so with this, let us stop here, and we will take up the high pass filters in the next class.